Okay, to maximize or minimize f of x comma y comma z subject to two constraints now. So we've got a function g sub 1 equal to constant k sub 1 and a function g sub 2 equal to constant k sub 2. There must exist scalars lambda and mu, which are called Lagrange multipliers, such that instead of gradient of f just equals lambda times gradient of g1, now there's a plus another Lagrange multiplier called mu times gradient of g2. So we will try this. This is quite a process. We're going to minimize x squared plus y squared plus z squared subject to y plus 2z minus 12 equals 0 and x plus y minus 6 equals 0. So we have two constraints. There are two equations after subject to. Just to reformulate, we've got f should be x squared plus y squared plus z squared, g1 is y plus 2z minus 12, and g2 is x plus y minus 6. So the original question can be repackaged as minimizing f, subject to the constraints that g1 and g2 are both equal to 0. Both equal to some constant. In this case, they both happen to be 0. So we'll compute gradients, and then we'll set up gradient of f equals lambda gradient of g1 plus mu gradient of g2. And in our case, this looks like this, right? 2x comma 2y comma 2z equals lambda times 0, 1, 2 plus mu times 1, 1, 0. If we go ahead and do the scalar multiplication of lambda and scalar multiplication of mu and add the vectors that are on the right side, now we set component y's, so 2x equals mu, middle component 2y is equal to lambda plus mu, and last component 2z equals 2 lambda. So we have these three equations, and we also actually have two equations at the top. Right away in the question, there were two constraints. Okay. Yeah, there's three equations so far, 5 variables, right? So I gave that away. The two original constraints gave us 2 more equations. So in the end, we have 5 equations, 5 unknowns. Okay, let's put them all at the top of the next slide. Okay, so separated by period, so I hope that's visible. 2x equals mu, 2y equals lambda plus mu, 2z equals 2 lambda, y plus 2z minus 12 equals 0, as well as x plus y minus 6 equals 0. 5 equations, 5 unknowns. Here we go. Lots of different ways to do this, but let's sub 2x for the mu and sub, 2z equals 2 lambda just means z is lambda, right? So let's just sub those into the second equation. So 2y equals lambda plus mu becomes 2y equals z plus 2x. Okay, the fourth equation, solving for z, is 12 minus y all over 2. And the fifth equation, solving for x, is x equals 6 minus y. So let's sub what we just got for z and x into the equation 2y equals z plus 2x. So we'll write 2y, okay? And then that's equal to, replace the z with the fraction 12 minus y over 2, and then plus 2 times, and then replace the x with 6 minus y. So finally, we have an equation that's all in one variable. This is, of course, not the only approach that works. You just have to do what you see first. But if you start substituting a little too circularly, you just get, equations like 3 equals 3 or whatever. So this equation only has one variable called y. I'll spare you the details. You should just get y equals 4 from it. With the fact that y equals 4 and x is equal to 6 minus 4, you get x is equal to 2. With y equals 4 and earlier how we solved for z, you're going to end up getting z is equal to 4. Okay, so the only solution we get is x comma y comma z is equal to 2 comma 4 comma 4. And we did not find either Lagrange multiplier. We could if we'd like to. We can just find it. Of course, from 2z equals 2 lambda, we know that lambda is equal to 4. And then if we wanted to get mu, let's see, 2 times x, so 2 times 2. Yeah, so I guess mu is equal to 4 coincidentally as well. We could find mu and lambda, but we don't need them. The point is, this one point is going to minimize x squared plus y squared plus z squared. We are done. Now, since it was the only solution, we didn't actually have to check f values. We could have computed the f value if we wanted. Now, how do we know that we found the min and not the max? That requires a more advanced Lagrange theory, so we're not going to go through it. We'll skip it. We're just going to trust that the equation was asked correctly. The question asked us to minimize.